indeterminate forms and L'Hopital's rule. In Calculus 1, we talked about indeterminate forms such that we were able to calculate the limit of an indeterminate form, and we talked about forms infinity divided by infinity, 0 divided by 0, infinity minus infinity, those types of things. Negative infinity divided by positive infinity, negative infinity divided by negative infinity, positive infinity divided by negative infinity. We call these indeterminate forms. If the limit is in an indeterminate form, then you can simplify to be able to calculate the limit by either factoring, if that's possible, or rationalization, if that's possible. And then thirdly, today we introduced L'Hopital's rule, which probably should be read Bernoulli's rule, because it was one of the Bernoulli brothers that actually proved this theorem. And L'Hopital wrote a book and he used Bernoulli's information. That was going on a long time ago as well. Well, so we use this plagiarist gentleman's theorem. Well, that might be a bad statement, but Bernoulli and L'Hopital were good friends. So L'Hopital's rule says that if you have a function, a rational function, f and g are said to be functions that are differentiable on some open interval ab containing c, except possibly at c itself. It does not necessarily, the function would have to be differentiable at c. And particularly, that's where we have a lot of the breakdown, where you get 0 divided by 0 or infinity over infinity. Assume that g of x is not the zero function for all x on this interval ab, except possibly at c itself. G prime of c may be 0, and that's why we have the problem and the breakdown. Hence, we have a special technique to try to overcome it. If the limit of f divided by g as x approaches c produces some indeterminate form, there they say 0 over 0, but it could be various indeterminate forms that are also stated down here. If you have that, and the key is that we have an indeterminate form, then you are able to look at the limit with of f divided by g as the limit of take the derivative of the numerator divided by the derivative of the denominator, and then examine that limit, and hopefully you can produce a worthwhile consequence. If not, if that limit gives you another indeterminate form, then take the derivative again. I don't think we have that case in this section, but I believe in the next section it's possible. Well, let's go ahead and look at some problems here. In these problems 5 to 10, evaluate the limit using a technique from chapters 1 and 3, and then also part B using L'Hopital's rule. So for part A, it looks like we can factor. Notice, but before you do that, let's go ahead and plug in x equal to -4. So when we do that, we get 16 times 2, so that's 32, and then we have that 32 plus the 20, and so that gives us 52, and then 13 times 4 is negative 52, is -4. So we get negative 52 plus 52, that gives us 0, and then -4 plus 4 downstairs is 0, so we get 0 over 0. So it's an indeterminate form, so because of that, we can factor, well, we can try. To rationalize means that you're looking for a radical. If there's no radical, then we try to factor. If you can't do that, then apply L'Hopital's rule. So let's see if that makes sense. So this is 5 and 8. That gives us 13. So we can cancel out. The limit as x goes to -4. This is just 2x plus 5. Now you can substitute x equal -4 into the limit expression. It gives us -8 plus 5. We get -3. Now part B says just use L'Hopital's rule directly. And most times L'Hopital's rule is a quicker way of getting the limit. So take the derivative of the numerator. So that's 4x plus 13 divided by the derivative of our denominator, which is 1. Now I'm plugging in x to equal to -4. So that gives us -16 plus 13, and that gives us -3. Obviously, parts A and B should give you the same result. So for number 7, this limit as x goes to 6, if you plug in x equal to 6, that'll give us the square root of 16, which is 4 minus 4, gives us 0, and then 6 minus 6 is 0. So this is, again, an indeterminate form. So here we rationalize. While we have it here, I'm just going to go ahead and just put what we need. Multiply to the numerator and denominator by the conjugate of our numerator. This is the limit as x goes to 6. Simplify the numerator. The first term, the first, will give us x plus 10. The outer times the outer minus the inner times the inner would cancel out. So we have left then times the last time the last, which is minus 16. Just leave the denominator as it is. So this gives us the limit as x goes to 6. The numerator becomes x minus 6. This is all over x minus 6 times the square root of x plus 10 plus 4. Now the x minus 6 cancels out upstairs and downstairs, and we have left the limit as x goes to 6 of 1 all over the square root of x plus 10, and then out here plus 4. Now we plug in x equal to 6. We have the limit of 1 over the square root of 16, which is 4 plus 4. That just gives us 1 over 8. That's part A. Now part B, we apply L'Hopital's rule. Take the derivative of the numerator divided by the derivative of the denominator. So we have the limit as x goes to 6. Take the derivative of the numerator. That gives us a 1/2 times the expression x plus 10 to the negative 1/2 times the derivative of the inside, which is just 1. The derivative of -4 is 0. That's divided by the derivative of x minus 6. That's 1. So we have the limit as x goes to 6 of 1 all over 2 times the square root of x plus 10. Now we plug in x equal to 6. Good. Well, this is a 2 here. It's not the square root of x plus 10. It's 1 over 2 times the square root. Just want you to make sure that 2. This guy won't let me erase just that. This cuckoo caca computer, right? We just plug in x to equal to 6, so we get the square root of 16, which is 4. So we get 1 over 2 times 4. And that gives us just 1 over 8. Okay, so here, plug in the limit. You get, as x goes infinity, you would get infinity divided by infinity. Okay. And so the instructions, see if you can factor. If you can factor, fine. Can you rationalize, that's fine. And then after that, we apply L'Hopital's rule. Now, we have a technique from Calculus 1 that says that when you're taking the limit here, and as x goes to infinity, you can examine the degree of the numerator divided by the degree of the denominator. A lot of D's in there. If the degree of the numerator is less than the degree of the denominator, then the limit, or the horizontal isotope, if you will, is equal to 0. If the degree of the numerator is the same as your degree of your denominator, then the limit, or the horizontal isotope, is the ratio of the leading coefficients, 5 divided by 3. And then the other case was that if the degree of the numerator is greater than your degree of your denominator, then the horizontal isotope is either a line, or depending on that term that's left from the division. But we say there that if x is going to infinity, that limit is going to be infinite as well. That is when the degree of the numerator is greater than your degree of the denominator. But here, the degrees of the top and the bottom are the same. So the limit, and I'm just going to go ahead and just go right to it, because we have that case from Calculus 1 and also from algebra. So here, the limit as x goes to infinity of this 5x squared minus 3x plus 1 all over this 3x squared minus 5. So this is, look at the leading coefficients, they're the same. So I just look at the degrees, they're the same. So I divide the leading coefficients, 5 divided by 3. That becomes your limit. Part B, use L'Hopital's rule. The limit as x goes to infinity, take the derivative of the numerator, we get 10x minus 3 all over 6x. You check this limit here, you still get infinity divided by infinity. So if that's the case, then we apply L'Hopital's rule again. I thought we wouldn't use L'Hopital's rule twice in this section, but we do. So here, this is the limit as x goes infinity of 10 over 6. Well, the limit of a constant is a constant. You simplify that, you just get 5 over 3. Here, evaluate the limit just using L'Hopital's rule. So we check. The limit here is x goes to 1 of the natural log of x to the third divided by x squared minus 1. You plug in this limit, and this gives you 0 divided by 0. So this is indeterminate, so we use L'Hopital's rule. This is the limit as x goes to 1. Take the derivative of the numerator. That becomes 1 over x cubed times the derivative of x cubed, so that's 3x squared. This is all over 2x, our derivative of the denominator. This is the limit as x goes to 1. We simplify that. So this is 3 over x divided by 2x. This is the limit as x goes to 1. And this is 3 over 2x squared. And that just gives us 3/2. Look at the next one. Again, apply L'Hopital's. You know something from algebra and from calculus 1. If x is going to infinity, then basically you're examining, in some sense, the horizontal asymptote. So if the degree of the numerator is the same as the degree of the denominator, man, these d's mess me up. So then your limit is just the ratio, the leading coefficients, 5 divided by 4. Okay. Well, let's check. You plug in infinity, you get infinity divided by infinity, right? So here we take the derivative of the numerator divided by the derivative of our denominator. So that gives us 10x plus 3 all over 8x. You plug in x as x goes to infinity. Again, we get infinity divided by infinity. So we take the limit again. Here, taking the limit, we apply L'Hopital's rule. Take the derivative of our numerator, we get 10. Divided by our derivative of the denominator, we get 8. The limit of a constant is the constant. You simplify, we just get 5 over 4. Okay. All right. Now, hopefully, using that technique from algebra with the horizontal asymptote, if the degree of the numerator is greater than your degree of the denominator, then the horizontal asymptote or the limit is infinity. Now we can apply L'Hopital's rule and you can get it as well. So here, this is the limit. This is infinity divided by infinity, or infinity squared divided by infinity, however you want to say it. So the limit as x goes to infinity, take the derivative of the top, we get 2x plus 4 divided by 1. This is the limit as x goes to infinity of 2x plus 4. And as x goes to infinity, 2x plus 4 also goes to infinity. Plug in x equal to 0, you get sine of 0, which is 0, divided by the tangent is the sine divided by cosine, so you get tan of 0 as well. So we get 0 over 0. So we apply L'Hopital's rule. So we get here the limit as x goes to 0. Take the derivative of the numerator. That's cosine 5x times 5. So we get 5 times cosine 5x. That's divided by the derivative of the tangent. It gives us secant squared 9x times the derivative of 9x. That just gives us 9. So we get 9 times secant squared 9x. Simplify that. This is the limit as x goes to 0. We know that the secant is 1 over cosine. So this is the limit of 5 over 9, which we could have put out in the front. And let's just do that. Times the limit as x goes to 0. This is cosine 5x all over 1 over cosine squared 9x. So this is 5 over 9 times the limit as x goes to 0 of cosine of 0 divided by 1 over this cosine squared of 0. Well, cosine of 0 is 1, and 1 over cosine squared of 0, that's 1 divided by 1. So this is 5 over 9 times the limit as x goes to 0 of 1. And the limit of a constant is a constant times the constant. We just get 5 over 9. It's a poor 9.
Yeah.
Let's see. I got 2 more pages to work. These are a little bit more into it. Let's take a break and then we'll come back and work the rest.